We want to use the integral test to determine if the following series converges or diverges. For the first step, we want to find a function f of x, or f of n, equals a sub n, the formula here used to generate the terms in the series. So f of x would be equal to 2 natural log x divided by x to the 8th. Now if we look at the notes on the integral test, the notes tell us that f of x must be positive, decreasing, and continuous on the interval from 1 to infinity, such that f of n equals a sub n. And if this is the case, then if this integral converges, the infinite series converges, and if this integral diverges, the infinite series diverges. But this function is a special case. If we look at the graph of this function, notice how it's actually increasing over this small interval here, but then it does decrease as x approaches infinity. So even though it is increasing over this small interval, we can still apply the integral test. So we want to find the integral from 1 to infinity of f of x integrated with respect to x. If this integral converges, the series converges, and if the integral diverges, the series diverges. Notice how we have an improper integral, so let's go ahead and factor out the 2 and write this as 2 times, we'll take the limit as b approaches infinity of the integral from 1 to b of natural log x divided by x to the 8th dx. And now to find the antiderivative, notice how we'll have to apply integration by parts. So let's let u equal natural log x. So if u is equal to a natural log x, notice that dv would be equal to 1 divided by x to the 8th dx, or we can say dv equals x to the power of negative 8 dx. And now we'll differentiate to find du. Du equals 1 divided by x dx. And we'll integrate to find v. So v would be equal to x to the power of negative 8 plus 1, which is x to the negative 7th divided by negative 7, or negative 1/7 x to the power of negative 7. So we have 2 times the limit as b approaches infinity of u times v would be natural log x times negative 1/7 x to the negative 7. Let's write that as negative natural log x divided by 7 x to the 7th. And then we'll have minus the integral from 1 to b of v times du. So v is negative 1/7 x to the negative 7th. And du is 1 over x dx, or times x to the power of negative 1 dx. Let's go ahead and simplify this. So we'd have plus 1/7 times the integral from 1 to b of x to the negative 8th. And now we'll find the antiderivative of x to the power of negative 8, which we actually already did when we were setting up our notes for integration by parts. Notice here, the antiderivative of x to the power of negative 8 is negative 1/7 x to the negative 7th. So we have 2 times the limit as b approaches infinity of, again we have negative natural log x divided by 7x to the 7th. And then here we have plus 1/7 times the antiderivative, which is negative 1/7 x to the negative 7. So we'd have minus 1 over 49 and then x to the 7th. Let's continue on the next slide. So when x is equal to b, we have negative natural log b divided by b to the 7th minus 1 over 49 b to the 7th. And then when x is 1, we have negative natural log 1, which is 0, divided by 1 to the 7th minus 1 over 49 times 1 to the 7th. Notice as b approaches positive infinity, this fraction here approaches 0. Looking at this first fraction here, this fraction also approaches 0 as b approaches infinity. We may need to apply L'Hopital's rule here to verify this, but the denominator is growing faster than the numerator. And again, natural log 1 equals 0, so this fraction would be 0, and this fraction here would just simplify to 1 over 49, which means we have 2 times, because we have minus negative 1/49th, it'd be 1/49th. So the improper integral converges to 2 divided by 49. So because the integral converges, the infinite series also converges by the integral test. So let's go ahead and summarize this. The integral from 1 to infinity of f of x, which is 2 natural log x divided by x to the 8th, integrated with respect to x, converges. So, by the integral test, the infinite series also converges. I hope you found this helpful.